This video is brought to you by the Environmental Protection Agency. The use of any trade names or commercial products does not constitute an endorsement on the part of the Environmental Protection Agency. The purpose of the video is to provide small water systems with an introduction to the use of an ion exchange as an arsenic removal technology. Ion exchange has been identified as a best available technology for removing arsenic from drinking water with low sulfate concentrations. Ion exchange is a treatment process that uses synthetic resin that exchange an ion for an unwanted ion in water. Many people are familiar with this process because it is often used in homes to remove hardness from water. In order to accomplish the exchange reaction, a packed bed of ion exchange resin bead is used and raw water is continuously passed through the resin bed until the resin is near exhaustion. If the resin is operated beyond exhaustion, breakthrough of the unwanted ion or ions will occur. When using ion exchange for arsenic removal, an anion exchange resin is used whereby negatively charged arsenic 5 ions are exchanged for chloride ions of the virgin resin. The exchange process is reversed by flushing the resin with a concentrated sodium chloride brine solution. This causes the resin to release the arsenic 5 and other anions by replacing them with chloride from the brine and prepares the resin for reuse. It is important to remember that only the oxidized form of arsenic, arsenic 5, can be removed using an ion exchange process. The process is not effective for the removal of arsenic 3. Equally important is the fact that most resins preferentially remove sulfate over arsenic and nitrate. The resin loads from the top downward with the flow of raw water. As the resin bed becomes exhausted, sulfate forces the arsenic and nitrate deeper into the bed. The treatment process must be stopped for regeneration of the resin prior to full exhaustion, or the sulfate can force nitrate and arsenic to be discharged into the finished water at concentrations much higher than in the raw water. This phenomenon, known as chromatographic peaking, can cause health risks, particularly so for nitrate, which is an acute contaminant. Because the water contains orders of magnitude more sulfate and nitrate than arsenic, the frequency of regeneration is dictated by the sulfate and nitrate concentrations. Ion exchange is being used at one of EPA's arsenic treatment technology demonstration sites located in Fruitland, Idaho. The treatment equipment and resin at this installation have been provided by Kinetico. The raw water is produced by a single well capable of up to 200 gallons per minute. The water contains about 35 micrograms per liter arsenic, 51 milligrams per liter sulfate, from 12 to 15 milligrams per liter nitrate, and has a pH of about 7.3.
Here in Fruitland, all of our water comes from groundwater sources, and each well will be above the new regulations that go into effect in January. Most of our arsenic ranges from 20 parts per billion to about 38 parts per billion. And some of our wells are fairly low in nitrate, but over 50% of the wells are high in what I call borderline in nitrates. They'll be anywhere from 6 milligrams per liter to 9 milligrams per liter.
The treatment process consists of a battery of 25 micron bag filters to remove sand or other sediment, 2 skid-mounted ion exchange vessels, and brine production and storage facilities for regeneration of the resin. The groundwater at Fruitland contains primarily the oxidized form of arsenic, arsenic 5. Therefore, pretreatment with an oxidant is not necessary, although some states might require chlorination of the treated water to ensure microbial quality. Fruitland selected the ion exchange because in addition to arsenic 5, it also removes nitrate, which is present at levels above the maximum contaminant level.
Probably will most likely have to use ion exchange because of the borderline nitrates. We don't want to put a capital expense into removing arsenic and then find out 6 months or 1 year later that that borderline nitrate is elevated and exceeded the 10 milligrams per liter, and therefore have to shut the water source down.
After passing through the bag filters, the raw water stream is split equally to flow from top to bottom, half through each resin-filled vessel. This is called a parallel configuration.
And the arsenic and the nitrate stick to the resin, come out the bottom, and away they go. And then in a regeneration, it also feeds from top to bottom.
Since the raw water concentrations of sulfate, arsenic, and nitrate are relatively stable, the process is predictable and has been adjusted such that regeneration of each vessel occurs after treatment of 335,000 gallons of water. When regeneration is called for, a portion of the raw water flow for one vessel is diverted through a venturi that pulls in a concentrated brine solution to be mixed with the remainder of the water and then pass through the resin. Chloride ions from the brine replace the sulfate, arsenic, and nitrate attached to the exhausted resin. Salt for regeneration is stored in this 19-ton container that is filled to the 6-foot mark with water to ensure a constant supply of brine.
There's a water level from the bottom to the top. It's right about, right in here somewhere. It's about 6 foot, 6'1". It'll vary from 6'1" to 5'7" on any given day. When you go into a regeneration, this valve will kick open off a timer from the computer. It'll fill this up to the demand need, and that's how you get your salt saturation brine for the regeneration.
The city of Fruitland uses from 6,000 to 8,000 pounds of NSF-approved salt per week at a delivered cost of about 10 cents per pound. The waste brine containing the arsenic and the rinse water is discharged to a floor drain from which it is transferred to the sanitary sewer. Waste brine produced by the ion exchange process may contain enough arsenic to be considered hazardous. Therefore, ion exchange is often more cost-effective when the brine can be discharged to a sanitary sewer. Ion exchange is also used for arsenic removal at Rimrock, Arizona. This system is a proprietary anion exchange process provided by Basin Water. The treatment vessels, pumps, controls, etc., are delivered to a prepared site in a shipping container that contains several vessels operated in parallel. The Basin Water system has been used at numerous locations for nitrate removal and is now being used for arsenic removal. Arizona Water Company has selected Basin's ion exchange for several sites because it was found through a bidding process to be the most cost-effective technology. Typically, all but 3 vessels are in production. 1 vessel is in standby mode, 1 in the process of regeneration, and 1 offline for regeneration.
It goes offline when it regenerates. At any given time, several of the beds will be out, up to 3 will be out in some sort of regeneration step, but the remaining beds, in this case we would have 7 remaining online treating. So as a bed regenerates, we don't have any reduction in capacity for the unit. The unit continues to operate.
One advantage of multiple vessels is that a more constant flow of finished water can be produced. The 2-vessel system at Fruitland loses 50% of its production for nearly 5 hours during regeneration. Since anion exchange also removes bicarbonate alkalinity, the multiple vessels staged regeneration approach provides finished water with a more stable pH and alkalinity. This can be important for lead and copper control. This system is controlled by a computerized system that can be accessed remotely. It reuses brine 3 times and uses rinse water for brine production, therefore reportedly produces a lesser quantity of waste. In some locations, the waste brine is passed through absorptive media that will remove the arsenic.
We have our adsorptive media in here. We circulate the waste brine solution across this media, and the arsenic then attaches to the media in here, and now we have a brine solution which is low in arsenic. The arsenic is left behind in these drums, and at that point the waste brine is then transferred to the waste tanks outside for disposal.
That media typically passes the toxicity, characteristics, leaching potential test. The treated brine is then hauled away for disposal. In summary, ion exchange may be a suitable arsenic removal technology for some small systems. It has the advantage of being able to remove other contaminants, including nitrate, and uses a relatively short empty bed contact time. However, chromatographic peaking is a potential risk, and large volumes of brine waste are produced. For more information on these and other EPA arsenic treatment technology demonstration sites, you can visit EPA's website at the address shown on the screen.